evening, everybody. This is the ABC of galaxy evolution. Now, we're all familiar with what galaxies are when we either look through our telescopes or perhaps download images from the Hubble Space Telescope. We see these wonderful structures. Some of them relatively amorphous blobs, but many of them are these beautiful spiral structures. And the question is, how did all of these galaxies come to be? So we're going to be looking at the ABC, the three factors that dominate the galaxy evolution process. Firstly, A is for accretion, because galaxies form by matter accreting or accumulating, if you prefer, under the influence of gravity, the matter that was created in the Big Bang. B is for black holes. Supermassive black holes at the centre of most, if not all, galaxies. Some are very active and are feeding on matter falling in from their surroundings. Others, like the one in our Milky Way, is more quiescent. And finally, the C stands for collisions, because galaxy evolution over the long term, over billions of years, is affected by collisions and by mergers between galaxies. So we'll be looking at each of these three in turn. So where does the story start? Well, the story starts at the beginning. And in this case, that means the beginning of everything. So back in January, I was talking about how the Big Bang in 3 minutes created all the matter in the universe. And I also described how everything that is currently inside the observable universe, a fraction of a second after the Big Bang, everything that we now see inside the observable universe used to occupy a volume no larger than a golf ball. Eventually, that golf ball expanded and the universe turned transparent, and the radiation released is what we now see as the cosmic microwave background. But the question is, how do we go from the golf ball and the cosmic microwave background, how do we go to this universe that seems to be full of 1 trillion galaxies? Well, pretty much everything we understand about the evolution of the universe on a cosmic scale, meaning let's not worry about individual stars here, but let's just think about galaxies and clusters and superclusters of galaxies. Pretty much everything we understand comes from simulations. So yes, we can think about what the laws of physics are, but it's only through doing simulations and comparing simulations with reality that we get a handle on understanding. So don't worry about the detail on the left-hand side here. This is just a reminder that there are lots of people doing lots of simulations trying to understand the structure of galaxies and the structure of the large-scale cosmic structure of the universe. In this particular talk, I've borrowed videos and images from a particular suite of illustrations called Illustris. Other simulations are available. I've just concentrated on one for the sake of simplicity. So the universe starts about the size of a golf ball, and there are variations. The dimples in the golf ball represent the variations in density that over billions of years collapse to form the structures that we see. And we can see that in a simulation. If we start with a cube of a given size, it doesn't really matter exactly how big this is. If we start with a cube full of matter and we put in very small variations of density and then let gravity do its stuff, over billions of years we see the matter collapse into a structure of filaments and voids. And we might call this the cosmic web, if you like. Matter streams down these filaments, and where filaments cross each other, you get these little high-density regions of matter. This is where the galaxies will form, these little white blobs, and we'll zoom into these in a little while. But for the moment, we see that where filaments intersect, that's where galaxies start to form. The densest part of the web are the nucleation sites for these clusters. Matter flows down the filaments and the accumulation of matter builds up, and that's where the early galaxies form. But we can't simply say, here's a load of matter, let's let gravity do its stuff. if we want the simulations to be realistic, then we have to take into account the fact that as matter comes together, stars are born. Stars live, stars die. They might die as supernova, they might form black holes, but there will be matter coming out. There will be gas expelled, as we can see in this particular simulation. These red bubbles represent gas being blasted out by supernova or by black holes, and that can impede the infalling matter. So it's not just a question of saying, let gravity do its stuff. If we want to get sensible, realistic output, we have to build in a lot of stellar physics as well. What we're trying to do is to get some handle on, can we understand why there is such a diversity of different galaxies? Here's a few hundred galaxies that have been imaged, and they've simply been put into this grid to indicate that some galaxies are relatively disk-like and tend to be coloured blue. A lot of them have spiral structure. Those are on the left-hand side. And over on the right-hand side, we see a lot of relatively amorphous, almost featureless galaxies, elliptical in shape, and they tend to be redder in colour. Can we understand this sort of diversity based on our simulations? So let's look at the first element of the ABC, the A for accretion. Before we look at the results of a simulation, let's just have a little think about the simulations themselves. The illustrious set of simulations, and the web page is down at the bottom if you wanted to go there and have a look at these simulations for yourself, where there are lots of videos and images provided for the public. This particular project is a set of simulations that run effectively from just after the Big Bang all the way to the present day. We could in principle go into the future as well, but what we want to do is to start from the conditions of the Big Bang and then say, after 14 billion years, do we get the sort of galaxies that we actually see at present? But along the way, we do have to take lots of other things into account. I've already mentioned the central panel there. We have to take into account the fact that stars are being born and stars are dying as these galaxies are evolving. So we have to take into account black holes and supernova. But another elephant in the room is the fact that the universe isn't simply full of hydrogen and a little bit of helium. There's actually a huge amount of dark matter. There's more dark matter than there is hydrogen, in fact. So we have to put that into the mix as well if we want this simulation to be realistic. So all of these factors have to be in there, and that's why these simulations are so complex. If it was only start with hydrogen, let gravity do its stuff, then the simulation wouldn't have to be too complex. But building in all of the stellar astrophysics as well means that the simulations themselves are rather complex. The illustrious simulations ran for approximately 20 million CPU hours, CPU just being central processing unit, computer hours if you will. And it ran over that period in the early teenies. That particular set of simulations were then followed by an even more sophisticated set of simulations. They tweaked all the parameters and realized that they could make the simulations more realistic and cover larger volumes. What did they call this? Did they call it Illustris version 2? No, they didn't. They called it Illustris the next generation. Yeah, Illustris TNG. And again, the web page at the bottom gives you access to the videos and images from this set of simulations. So from now on, I'll just refer to the TNG simulations, shorthand for the Illustris next generation simulations. These TNG simulations ran for 10 times as long, 200 million CPU hours over the last few years. These simulations were carried out on a Cray supercomputer. If you wanted to run this sort of simulation and do it yourself on your own PC, well, in principle you can do that, but the program will take approximately 20,000 years to run to give you the sort of results that we're looking at this evening. The simulations were carried out on various spatial scales, so a cube of space, 300 megaparsecs on a side, was taken to give the large-scale structure. That's the image shown on the right. Although these are shown as squares, the whole simulation was carried out in a full three-dimensional cube. and 300 megaparsec gives you a good idea of what the large-scale structure of the universe looks like. But if we want to look at individual galaxies, we really need to home in and look in more detail at smaller scales. So in the bottom left there, TNG 50 looks at structures within a cube of 50 megaparsecs on a side. And TNG 100 is just the middle ground there, like 3bears, just to make sure everything is okay. So to remind ourselves that a parsec is about 3 light years, so 50, 100 and 300 megaparsecs are equivalent, or approximately, to 150, 300 and 1000 million light years. And if we just pause for a second and remind ourselves about parsecs and light years, yes, most astronomers prefer light years, but most astrophysicists prefer to use parsecs. And if we remind ourselves that the Milky Way is something of order 150,000 light years in diameter, that's approximately 50 kiloparsecs. And again, it's a useful rule of thumb to say that typical distances between stars is about a parsec. And if we think about how far apart galaxies are, let's just take the Milky Way and Andromeda as a yardstick. That distance is about 2.5 million light years. That's just a little bit less than a megaparsec. So that's all we really need to remember, that typically distances between stars are parsecs, and typically distance between neighbouring galaxies might be megaparsecs. That's the only thing we really need to remember about these units of distance. So let's have a look at the evolution of a particular galaxy taken from a TNG simulation. Here we're looking at the junction between different filaments which are coming in from the top right, the bottom right and the bottom left. So we're watching matter falling in from these filaments and starting to collect and accumulate and accrete in this central region. And you can see it's pretty chaotic, it's fairly messy, but generally speaking, as the billions of years go by, and this is quite a few billion years we're watching here, more and more matter is accumulating towards the centre of this particular image. The brighter the intensity of colours here, the denser the material. And you can see the density towards the corners is starting to decrease. It's getting darker and darker towards the edges, and as more and more matter is being used up and is funneling down into this central region. And you can already start to see, although it's still taking a little while to settle down, you can already start to see spiral structures within this galaxy starting to form. And the spatial scale on the left-hand side, you can see that space bar there is 50 kiloparsecs, so you can see this is a typical size of a spiral galaxy. What about simulation versus observation? If we look at the large scale, so the reversed image in the background there with the dark features on the light background, that's a full simulation from TNG 300. And if we zoom in to particular areas, we can see particular galaxies or pairs of galaxies, and we can ask ourselves, well, if this is what the simulation tells us, that the large-scale structure of the universe is this cosmic web of filaments and voids, but where the filaments tend to cross each other, that's where galaxies start to form. Do these simulated galaxies look the same as real galaxies? Well, one thing we can do is to look at these simulations and ask ourselves, are there any galaxies that we can see in the sky from the Hubble Space Telescope or elsewhere that look anything remotely like the galaxies in the simulation? And that top galaxy does indeed bear a resemblance to, in this particular case, the antenna galaxies. And the second pane there in the simulation does indeed bear a resemblance to interacting galaxies that we can see. So yes, we can do large-scale simulations and the galaxies seem to bear a reasonable resemblance to what we see in the sky. But what we really need is to look with higher resolution. We don't want to look on the largest scales if we're interested in individual galaxies. We want to look at the scale of 50 megaparsecs, the smaller boxes, to find out whether or not we can get detail of individual galaxies. So if we look at the output of TNG 50, 50 megaparsecs, if you think of a cube 50 by 50 by 50, that's an awful lot of galaxies in there if they're separated by a few megaparsecs each. So there's thousands of galaxies within one simulation, and here's a few of the spiral galaxies that are shown on the left-hand side. They're coloured according to where the highest concentrations of hydrogen gas are. And if we assume that that hydrogen gas is going to make stars, and we can calculate, roughly speaking, how much hydrogen generates how many stars, then we can predict what would those galaxies actually look like if we were to look at them in the visible part of the spectrum. And the right-hand side there, the grayscale images, show you what we think those galaxies would look like if the hydrogen made stars the way we expect them to. And perhaps you've looked at a few galaxies yourself through a telescope, or at least you've looked at various pictures of galaxies taken by larger telescopes, and on close inspection it looks like most of the galaxies that are generated in this simulation are analogues of the sort of galaxies we can see in the sky. Not only that, but the simulations produce galaxies with masses of something of order 100 to 200 to 300 billion stars of a similar mass to our Sun, and these galaxies look a lot like the Milky Way. So this particular example there, the face view, the face view of the spiral looks very similar to what we think our Milky Way galaxy looks like, and the edge view at the bottom there, two fried eggs back to back, that's pretty much what we think our Milky Way looks like in terms of a central bulge and then the thin disk containing the spiral arms. So if these simulations are capable of producing galaxies similar to the Milky Way, then again we think we might have it right. Certainly the opposite is true. If we run a whole load of simulations and the simulations do not generate galaxies of a sort of size and structure and shape as our Milky Way, then there must be something wrong. Because if we can't generate our own galaxy, how do we think this simulation is going to possibly generate other galaxies? So let's have a think about the second element of the ABC. The B is for black holes. Black holes at the centres of galaxies. So how do we know what lies at the centre of a galaxy? How do we know what lies at the centre of our own Milky Way galaxy? That's relatively close compared to most other galaxies, so let's look there first. We can look at stars orbiting near the centre of the Milky Way. That's not actually very easy to do because it's such a dusty environment. We can only do that by looking in infrared to cut through all of the dense material surrounding the galaxy in order to see what's going on around the centre. But when we do that, we find that there are stars orbiting close to the centre of the galaxy. Those stars are orbiting quite quickly, but what are they orbiting? We can't see anything that they're orbiting, but they must be quite massive in order to throw these stars away and get them to orbit in a period of only a few years. So there's something very massive but invisible at the centre of our Milky Way, and we deduce that must be a black hole. Over something of order 10 years or more, large telescopes here on Earth have monitored the positions of stars. Here's a number of them, just labelled star 1, star 2, etc. And by monitoring the positions of these stars and looking at the elliptical orbits that they map out, we can deduce what must be the mass at the centre that is keeping all of those stars in their orbits. And we deduce that the mass that's there is not simply the mass of a star like our Sun, or even 10 or 100 times the mass of our Sun. There's an object there with a mass of 4 million times the mass of our Sun. The symbol I've used in the bottom right there, M circle dot, that is simply shorthand for the mass of our Sun. There's nothing particularly special about the mass of our Sun, it's just a more convenient unit than talking about kilograms. So not only is it very massive, it also must be quite small. None of these stars have collided with this object, so the object must be smaller than any of those orbits, and we deduce that the object itself can be no larger than our solar system. And yet it has a mass of 4 million times the mass of our Sun. So it is definitely not, for instance, a star cluster that these are orbiting around. The only object that fits the bill of having that larger mass in that smaller volume is a supermassive black hole. So we deduce, I'll be using SMBH from now on as the acronym for supermassive black hole. There is one of 4 million solar masses at the centre of our Milky Way. And by looking at star motion in other galaxies, we can deduce the size of the supermassive black hole in other galaxies. For instance, Centaurus A, we can't see it in this particular image, but there is a black hole at the centre of Centaurus A of order 100 million solar masses. Now, any object, such as a star, that comes too close to a black hole can be shredded by the tidal forces of the black hole itself. Notice that the star doesn't simply get pulled into the black hole itself. In much the same way that if you let water out of a bathtub, the water doesn't immediately go down the plug hole, it tends to swirl, as it were, waiting its turn before going down the plug hole. Same for matter being sucked into a black hole. Most of the matter ends up in an accretion disk swirling around the black hole, and this so-called accretion disk gets very hot, and so the accretion disk radiates electromagnetic radiation. So when we talk about seeing black holes in the distance, we're not actually seeing anything coming out of the black hole, we're seeing usually the accretion disk of matter falling into the black hole. It's a very efficient way of converting matter into radiation. In addition, you notice that some black holes produce jets, very energetic particles that are shot out apparently of the north and south poles of the black hole, and the mechanism by which that happens, it's assumed to be related to the very strong electromagnetic fields that exist close to the event horizon of a black hole, but the mechanics are not fully understood. If we look at one of those jets in the galaxy M87, there's the entire galaxy and the jet in the centre. If we blow it up a little bit with a Hubble Space Telescope image, we would expect jets to be coming off in opposite directions in the way I've indicated in that previous little cartoon. In this particular case, what's happening is one of those jets is directed towards us and one of the jets is directed away from us. And a lot of the radiation in these jets tends to be directed in the direction of the jet itself. So the jet that's pointing roughly in our direction appears very bright, but the jet that's pointing away from us, most of the radiation is actually travelling away from us, and so the jet is actually too faint to see. But we think there are a pair of jets, just as indicated in the previous cartoon. In terms of trying to see a black hole, perhaps you've heard about the results of the Event Horizon Telescope a couple of years ago. Not a single telescope, but an interferometer based on linking together lots of radio telescopes around the world in order to image the accretion disk that's around the black hole in M87. And the black hole itself is known as M87 star, and what we're looking at there is the accretion disk surrounding the black hole. And it's thought that the black hole in this particular galaxy is some 6.5 billion solar masses, substantially larger than the black hole at the centre of our Milky Way. So what do we think we're looking at when we see this, as it were, donut surrounding this dark region? Well, this little cartoon, this little simulation gives us an idea. The accretion disk seen from above just looks like a pancake, and the accretion disk seen from below looks like a pancake. But if we look at the accretion disk from an angle, what we might expect is something that looks a little bit like Saturn's rings. But it's extremely distorted around a black hole simply because the black hole is distorting space, or if you like, the light is being distorted by the extreme gravity of the black hole. So although we can think of this as being a flat pancake like Saturn's rings, what's actually happening here is we can see the other side of the pancake, we can see the other side of Saturn rings because the light is coming over the top and bending over the top of the black hole. At the same time, we can actually see the underside of the ring as well, which is the bottom part of that image, because again the light that's coming from that distant part of the ring is being bent by the black hole. And there's a so-called shadow region in the middle where no light can be seen. The black hole is in the center of that central region, and there's a region about twice as large as the black hole itself from which we can't expect light to reach us because the light path would be bent so dramatically by the strong gravity of the black hole itself. We can get an idea of just how much energy is generated in one of these supermassive black holes by looking at a rather distant galaxy called Hercules A. There's Hercules A, a rather large and perhaps boring elliptical galaxy which doesn't seem to have much in the way of structure. It's quite large. To give an idea of scale, we can imagine that that little spiral galaxy there, if the Milky Way was at that sort of distance, then that would be approximately what the size of the Milky Way was. So we can imagine that as a sort of yardstick. Let's just imagine that spiral galaxy is the Milky Way sitting next door to Hercules A. So Hercules A is substantially bigger than the Milky Way. But what's impressive is not what we see in the visible from this Hubble picture. What's impressive is what we see in the radio. And in this particular case, if we add in the radio taken from the very large array, and recently LOFAR has produced some high-resolution images which look very similar to this. But we can see these two huge lobes which are originating in the supermassive black hole at the center of the galaxy. But you can see that particles shot out from that tiny region in the galaxy are actually producing things that we can see over enormous distances. You can see 10 or 20 times the size of the Milky Way. These jets are penetrating into the intergalactic medium and producing these shock waves that we can see there. So the amount of power that's pouring out of that tiny black hole in the center there is truly astounding. If a supermassive black hole is feeding voraciously on the surrounding gas and stars and anything else that falls into the black hole, then we call that an active galactic nucleus, or AGN. And the most energetic AGNs that we know of are called quasars. These emit so much radiation, so much light, that they can be observed from distances of many billions of light years. Arguably, they are the brightest objects that we can see. And the subject of a rather different talk, during a lockdown, I tried to image one of these quasars, not using a telescope, but just using my camera and a telephoto lens. And this quasar, despite being at a distance of 25 billion light years, it was possible to pick it up using a camera. So that tells us that the amount of light pouring out of this quasar must be absolutely huge. The distance, 25 billion light years, is so great because of the expansion of the universe. The distance to this particular object is such that the recession velocity of this quasar would be something like twice the speed of light. It's that far away that it's receding from us at twice the speed of light. And despite that, you can pick up its light using a camera without even needing a telescope. Excuse me, I've just showed there, okay, it's not the most impressive image ever taken. That's an extreme zoom into the quasar. It's just a pixel in the image, but the fact that you can image the light from such a distant object tells you just how bright quasars can be. So, supermassive black holes have been found in a very large number of galaxies. It's currently under debate whether or not they are in every galaxy or simply the majority of galaxies. But if we take quite a number of galaxies here and plot the mass of the black hole on the vertical scale versus on the horizontal scale the mass of the galaxy it's in, strictly it's not the mass of the galaxy, it's the mass of the galaxy that's in the central bulge of the galaxy itself, then we find there's a relationship between the two. Smaller galaxies, such as for instance the Milky Way doesn't have a particularly large bulge at its centre, and it has a relatively modest sized black hole of order a few million solar masses. Whereas a relatively large galaxy like M87 has got a supermassive black hole of billions of solar masses. And you can see this relationship between the two. But just because we know there's a relationship doesn't mean we understand what the black hole is actually doing. It's a little bit of a chicken and egg problem. In the very early universe, did we find supermassive black holes start to form and then galaxies collect around them? Or did galaxies form and then supermassive black holes start to form at the core? Did they evolve side by side, or did one start and then the other join it? The best way of finding out is to look back in time to the very early universe, to the first fraction of a billion years of the universe's existence, and start to see whether or not we can see galaxies evolving the way we would expect them, based on black holes forming early or perhaps black holes forming late. We need more simulations, and we need more observations that go back more than 13 billion years so that we can see. What about the third element of the ABC of galaxy evolution? C is for collisions, because galaxies grow by colliding and merging. They form in the first place by accretion from the hydrogen that existed in the early universe, but they grow by collisions and by mergers with other galaxies. So when we look at a static image like this, and we look at a galaxy, beautiful though it is, it can give us the false impression that galaxies are rather static. Yes, we know that they're rotating, but we know they take hundreds of millions of years to rotate. So we get the impression that that galaxy looks pretty much the same now, and it looks pretty much the same in a billion years' time, we think. However, we can't sit and watch it, but again, we need simulations in order to understand exactly how galaxies interact with each other. Yes, we can see snapshots. The more individual pictures we take with Hubble or other ground-based telescopes, the more images we take of galaxies, the more we see that it's quite common for galaxies to interact with each other and produce tidal forces which can interrupt the evolution of a single galaxy. But the full influence of exactly how collisions and mergers affect galaxy evolution, that can really only be appreciated if, again, we run simulations to try and understand how they work. And here's an illustrious simulation of a few megaparsecs of galaxies, and you can see it is a chaotic soup of galaxies. Far from being individual and non-interacting, the more you watch this, and I've watched this individual video quite a few times, the more you watch, the more interactions you see. In the centre, you can see two big galaxies merging together. They've just passed through each other, and now they've merged together to make one monster-sized galaxy. And there are lots of other smaller galaxies around. So we can run simulations like this, and we can ask ourselves, well, is the number of large galaxies to small galaxies about right? Are these simulations telling us that that's what we would expect to see? When we look at the Milky Way, it's surrounded by what we thought a little while ago was maybe a dozen or two small satellite galaxies. But these simulations would seem to be telling us that we would expect big galaxies to be surrounded by hundreds of smaller galaxies. So the question is, are the simulations wrong? Turns out maybe not, because it looks like we've simply missed some of the fainter galaxies. Now that we have got better instrumentation and better telescopes, we're finding more of these faint satellite galaxies around the Milky Way. So it looks like these simulations are a good indication of what we would expect. Let's just run that simulation one more time. The more we watch, the more we see. We see some galaxies interacting and merging. A galaxy coming in from the bottom. They are slowly moving towards each other under their mutual gravitational attraction. And in just a few moments, there we go, we find them whipping round each other. And now they're about to merge with each other. And over a period of millions of years, perhaps even billions of years, they have merged into one larger galaxy. And the more you watch this sort of video, again, I invite you to go to TNG website at the bottom there, where they have lots of these sorts of videos. You can watch the interactions and realize that some galaxies are getting ripped apart, but quite often a lot of galaxies are merging together to make larger and larger galaxies. Whenever we see a static image like this taken with the Hubble Space Telescope, whenever we see a galaxy cluster, they tend typically to look like this. Lots of relatively amorphous elliptical galaxies, which tend to be redder, and a relatively smaller number of the bluer galaxies, which seem to have spiral structures. And we think we understand this based on, again, looking at the results of simulations. Whenever we're looking at a galaxy cluster, we have a relatively crowded environment. And the more you crowd galaxies together, the more likely collisions are going to be. And it looks like whenever spiral galaxies collide, they tend to lose their spiral arms, and you end up with something which is probably more like an elliptical galaxy. So over time, even if you start with a cluster which contains lots of spiral galaxies, by the time all of these galaxies have interacted with each other, you will find more and more of them will end up as the redder elliptical galaxies rather than the bluer spiral galaxies. In the case of much closer to home, we're not in the middle of a particularly crowded area of our galaxy cluster, but the Andromeda Galaxy is going to collide with the Milky Way. If we look at this particular simulation, then if we run the video, Triangulum Galaxy is in the top left as a spectator, but now we can see the galaxies colliding. You can see the clock in the bottom right. As these galaxies get close, they will pass through each other. As they pass through each other, it's very unlikely that any particular star will collide with another star, but you can see the tidal effects of the gravity of the two galaxies disrupts the spiral structure, and they merge, they go through each other one more time and then gradually settle down into a new structure which has essentially no spiral arms and looks for all the world like an elliptical galaxy. So we think this is going to happen. The timescale there tells you it's going to happen in about 5 or 6 billion years. The collision will start a little bit before that, at about 4 billion years. We can imagine what it's going to look like. At the moment, we have the Milky Way in our sky, effectively the spiral arms as seen from the inside, of course, and there, just left of centre, top left of centre, is the Andromeda Galaxy. If we fast forward 1 billion years, things won't look that much different, except that Andromeda Galaxy will be closer, and so will be a larger chunk of our sky. Excuse me a second. What do we think it will look like when the Andromeda Galaxy gets closer still? 3.7 billion years into our future, we still have the Milky Way visible, and we still have Andromeda looking pretty much the same. In other words, the tidal effects whereby the gravity of one galaxy starts to disrupt the structure of another galaxy, that tends not to happen until the galaxies get relatively close to each other. So even at this point, when the Andromeda Galaxy is occupying a very large chunk of our sky, a wonderful target for astrophotographers in 3.7 billion years' time, but even at that point, the disruption of both galaxies is minimal. But if we work a little bit further forward, only another 100 million years or so, then all hell breaks loose. Now the two galaxies are starting to pass through each other. Remember, individual stars are unlikely to collide. The possible likelihood of two stars actually colliding with each other, out of 100 billion stars in both galaxies, perhaps 1 or 2 stars might actually collide with each other. But on the whole, the stars will simply pass each other, but in the process, all of the gas in one galaxy will pass through all of the gas in the other galaxy, and that will stir up the hydrogen clouds in both galaxies and will prompt a new generation of star formation. Hence we see these pink regions here, which are the hydrogen clouds, the stellar nurseries of the next generation of stars. That's at 3.8 billion years. 3.9 billion years, absolute chaos and star formation absolutely everywhere. So we should never think of galaxy collisions as being the end of life of a galaxy. Far from it. You can think of galaxy collisions as being a sort of rebirth, because it tends to produce new star formation. After 4 billion years, as we saw with that earlier simulation, the first thing that's going to happen is the galaxies pass through each other and come out the other side. And so at about 4.0 billion years into the future, the Andromeda galaxy has passed through the Milky Way, and most of the stars have carried on and gone through the other side. We can't be absolutely sure. You can't pick out one star and say that star definitely belongs to the Milky Way or belongs to Andromeda, because there will be an awful lot of star swapping at this point. And you can see that the spiral structure of the Andromeda galaxy has now been disrupted by its passage through the Milky Way. It'll then take a little bit of time to settle down, again, just like we saw in that earlier simulation. And at this point, some 5 billion years into the future, there are still 2 nuclei. The whole of the combination, what do we call the combination of the Milky Way and the Andromeda galaxy once they are one galaxy? Well, we'll need a new name. Do we call it Milkdromeda? Do we call it Andrilke? Do we call it Androway? I don't know what its name is going to be. We've got plenty of time to think about that, of course. But at this particular point, 5 billion years into the future, we now have one large galaxy which doesn't have any obvious spiral arms anymore. It looks like one large elliptical galaxy which seems to still have 2 nuclei. In other words, the supermassive black hole that was in the centre of the Milky Way and the supermassive black hole which is at the centre of the Andromeda galaxy, somewhat more massive than the Milky Way version, they seem to be still 2 separate nuclei. And it will take a little bit of time. They're probably evolving around each other. It's not going to be a perfectly head-on collision between these 2 galaxies, so almost certainly it'll be more of a slightly glancing blow. These 2 supermassive black holes are going to be orbiting around each other, and it will take a long time before they merge into one huge supermassive black hole. That could take quite a few billion years after this particular point. But it is quite possible that the black hole that will exist when the Milky Way and the Andromeda galaxy collide in a few billion years' time, that black hole could easily be feeding on all of the surrounding material and all of the stars in the vicinity. The collision of 2 galaxies is such a chaotic process that it is very likely that the resultant supermassive black hole will have a lot of matter falling into it. And remember, these are the conditions we need to make an active galactic nucleus. It's been hypothesized that, depending on how it goes, it might be that the Milky Way-Andromeda collision could actually form a quasar in our far distant future. Remember that quasars are visible even if they're on the other side of the observable universe. They're still visible without a telescope. So what would it be like to have a quasar on our doorstep, in our galaxy? Well, I guess we don't have to worry about it too much, because the sun will have puffed up to a red giant by then, and the Earth will have other problems to worry about rather than the Milky Way Andromeda quasar. But it's interesting to think about what it may look like in a few billion years' time. So I've been describing the ABC of galaxy evolution, the 3 factors which dominate the evolution of galaxies over the lifetime of the universe. They're formed because gravity produces an accretion of matter, or an accumulation of matter if you prefer. All of the hydrogen made in the Big Bang, and a whole load of dark matter as well, end up accreting under the influence of gravity, and where the filaments of the cosmic web intersect, that's where we get the largest density, that's where galaxies start to form. We still don't fully understand the role of black holes. We know that supermassive black holes exist at the centre of many galaxies, and some produce active galactic nuclei and quasars. Luckily, our Milky Way doesn't appear to be like that. No matter of any consequence is falling into the central black hole in our galaxy, so everything is nice and quiet. but we still don't fully understand the symbiotic role between black holes and the galaxies in which they live. And finally, one of the most important aspects of how galaxies evolve over billions of years, after they have initially formed, it is the collisions between galaxies and the mergers of galaxies that dictate how galaxies change over billions of years. And the simulations that I showed earlier in the talk help us understand that process and help us understand the diversity of galaxies that we see when we look out into the observable universe. So next time you're looking at a galaxy, whether it be a galaxy through a small telescope, or whether it be a galaxy imaged by a large telescope on Earth or the Hubble Space Telescope, next time you see a galaxy, especially a beautiful spiral galaxy or galaxies interacting with each other, I hope you remember the A, B, C. Thank you all for listening.